Welcome back to our course on scanning electron ion probe microscopy in material characterization. So, now we have been discussing on atomic force microscope, we have discussed on different modes of operation and also resolution, artifacts, noises, all this we have discussed, particularly the resolution of atomic force microscope. Lateral resolution also depends on the vertical resolution. In addition to that, the resolution depends on the tip size, but tip size small enough is not only good enough, it is also important to have a good vertical resolution and also the smoothness of the surface to get high resolution. For the this happens with a contact mode, but for the non contact mode the resolution depends on the distance between the tip and sample and other factors. Today those things we have discussed before. Today we will discuss some of the additional properties that can be measured using atomic force microscope. We have several kind of forces exist on the surface of the sample, and by measuring those forces by using a tip, AFM tip, we can measure a specific properties of the sample surface. Some of those we will discuss today. As per the different force between tip and sample is concerned, we can we can put those forces into two categories. One is long range force. Long range force are mostly attractive force. Those include van der Waals force, capillary force, electrostatic force. Electrostatic force can also be repulsive, but it is mostly long range order and mostly attractive force. And we have magnetic force. These are long range force we can measure, we can use in atomic force microscope to get specific information. For example, we are using van der Waals force for getting topography. We can use capillary force to measure the capillary force also we can measure, and we can use magnetic force to study the magnetic sample. For example, the sample is very smooth, but completely smooth, but there is magnetic features are there, magnetic features are present on the sample. So, using a magnetic tip in the AFM, we can tell how the magnetic contact on the surface is distributed on the sample, even though the sample is perfectly smooth as far the height is concerned. Similarly, we have short range force. Short range force include frictional force, adhesive force, and also the chemical bonding that are also exist on the sample surface. As per the van der Waals force is concerned, we know the van der Waals force F van der Waals force is, we have discussed this, VdW, which is equal to minus HR. R is H is Hamaker's constant, and which is constant, which is in the range of electron volt, around 1 electron volt, a few electron volt depending upon the sample, solids, etc. And R is our tip radius, and D is our distance between tip and sample, between tip and sample. So, this is what we have seen, this how van der Waals force is, van der Waals force changes as per the tip and also distance between sample and tip. Particularly with increasing the distance, this force will decrease, and also by having a larger tip radius, we have a force will can increase. This is what we have discussed before. For example, if a tip of radius, let us say this is, let us say 10 nanometer, and separation D is, if let us say 1 nanometer, then our Hamaker's constant can be around can be found at 1.6 electron volt. So, this is happens with a long range attractive forces. Then we have repulsive forces. Repulsive forces arises due to the Pauli repulsion, the electron clouds of the atom and the tip and the atom at the sample surface. When they overlap, there will be, as per the Pauli explosion principle, the number of that means there is only 2 electrons can be placed in one states, and therefore, as those are filled, other electrons which are coming to overlap, they will be reflected, or they will go away from the other atoms, and thereby repulsion occurs. So, at the end the attraction and repulsive forces etc., we have discussed on the basis of Lennardt's potential before, and those taking the Lennardt's potential curve, we have discussed about the attractive and repulsive forces, and in those cases the potential was described on the basis of two atoms, neutral atoms coming closer to each other. First they were much away from each other, then attractive force, then repulsive forces. But actually there are hundreds of atoms involved here, not the models we have utilized before. There is two neutral atom, but actually in the tip of the AFM tip there are few atoms, and the surface there are several atoms present. So, therefore, interaction is not only atom to atom basis, but also between several atoms. Therefore, it is more complicated than what we have discussed using the potential curve. If we look at the long range force, van der Waals forces, then that force, as you see here in this graph, that varies with different medium and different varies with also probe distance. As the probe distance increases, the force is decreasing in almost in all medium, and but also in the vacuum we see the force is much higher than a particular medium. So, the van der Waals forces decreases when we use a particular medium, and certainly through the distance it also decreases. Then if we look at the capillary force is one of the long range force, and when an AFM tip which is hydrophilic in nature brought close to the surface of the water layer, then a meniscus formed between the tip and sample. When tip is far away, there will be no capillary force or zero capillary force. When the tip comes close to the sample surface, when it is almost touched, then the water will wicks at the tip place, and water it will form a meniscus bridge. Meniscus bridge will form between the tip and sample, and that is what you see here. It is forming a meniscus bridge here, and that is our capillary force. And this capillary force is a long range, it is a long range force, and it is stronger than van der Waals forces. Therefore, in many occasions this capillary force will actually marks the other properties of the sample surface. And thus, when we are doing the atomic force microscopy under ambient condition, this capillary force will also come into picture. We actually will not able to measure the van der Waals force, though theoretically atomic force microscopy can function in any environment, but when we do in under environment condition, always a water layer present on the sample surface, and when water layer present on the sample surface, then sample is being covered by a water layer, or sample surface is being masked by a water layer surface, and we actually will not measure the correct van der Waals forces. So, the magnitude of the capillary force depends on the surface properties and also the tip, hydrophilic nature or hydrophobic nature, humidity, temperature, geometry of the tip. So, these are the different factors on which the capillary force depends, and the capillary force can be also described with a Laplace equation. As per the Laplace equation, F capillary force is equal to 4 pi r cos theta divided by 1 plus d by d. Here we know that r is the tip radius, and gamma is the surface tension of water, and theta is the contact angle between the water vapor interface and the tip, water vapor interface and tip, and d is the distance between tip and sample, distance between tip and sample, and small d is the length of the tip. Small d is the length of the tip that extend into the water, into the length of the tip extends into the water bridge. So, this is the capillary force on the sample surface. By knowing these values, we can know these values. Actually, we can measure these all these values required for to measure the capillary force. We can actually measure the capillary force on different sample surface and on different type of tip, whether it is a hydrophilic tip or other kind of tips. We can measure the capillary force. Then we have electrostatic force. It is another long range force, and electrostatic force exists between two conducting sample, conducting tip and the sample. They have to be conducting, and when there is a potential difference, when there is a potential difference, there will be electrostatic attraction. So, that electrostatic attraction will gives us the electrostatic force, this if the distance between the flat surface and there is a spherical tip with radius r, which is smaller than spherical, the distance between the tip, that is d, is smaller, distance between the tip and sample is smaller than the radius of the tip. Mostly our radius of the tip in AFM is 5 to 10 nanometer, and distance between them, distance between the sample and tip is in the few nanometer, less than 5 nanometer, and in that case we can use the electrostatic force using this equation, which is equal to where epsilon 0 is the permittivity of the free space, of free space, and r is our the tip radius, u is the potential, and d is the distance between tip and sample. So, the electrostatic force is the major force component when AFM is operated in the liquid, because in the liquid we have a charge, ions are there. So, there will be a charge on the sample surface, there will be charge on the tip, there will be electrostatic charge, and in the liquid there is no capillary force. So, in order to avoid the capillary force, the measurements can be performed in the liquid or in on a dry environment. But here, as there is no capillary force when both tip and sample are immersed inside a liquid, charge is built up, creating two electrical double layer, one on the tip and one on the surface, resulting in electrostatic force, which can be attractive or repulsive or 0 depending on the nature of the sample and medium. So, we can measure the electrostatic force using the atomic force microscope. Then another important microscopic techniques is the lateral force microscopy or frictional force microscopy, or FFM or LFM. This is a contact mode of technique, that means sample must have to be in contact, the tip must have to be in contact with the sample, and it is used to study the tribological properties of the surface. And the frictional force is related to the loading force. Loading force we apply vertically on the sample through the tip, and then we are putting a force vertically in the z direction, but due to the lateral force of the sample, the tip may bend, and this moment in the horizontal direction is the lateral force, and in by measuring the deflection of the cantilever in the horizontal direction, in the vertical direction we are measuring the z position, height of the sample, that is what the primary measurements in our AFM. We are measuring the height of the sample at every places location of the sample, then from there we are creating the 3D image. The deflection we are measuring through our cantilever deflection is upward or downward. So, in that way we are creating height features or height image, which is the topography image. In addition to that, remember in AFM we are not first we are in regular topography image, we are not measuring the displacement in the horizontal direction, we are only measuring the displacement in vertical direction. But when the tip is in touch with the sample, there will also be a lateral force or frictional force that will make the tip to bend horizontally, and by measuring that lateral force we can know the friction properties of the sample surface. That is why it is called frictional force microscopy or lateral force microscopy. So, in the lateral force microscopy, the lateral deflection of the cantilever, which is the result of the applied force given to the cantilever and when it moves in the horizontal direction, and the magnitude of this lateral force depends on several factors due to frictional coefficient, topography of the sample surface, and the direction of the cantilever moment, in which direction the tip is moving, in the left to right or right to left, and the cantilever lateral spring constant. These factors play important role and how much lateral moments will occur, and this is used to study again inhomogeneous sample. Like when there is a inhomogeneous sample, the friction properties of two different samples cannot be same, and thereby by measuring the frictional properties we can know that there is a inhomogeneity of the sample if there is no height difference. If there is a height difference, certainly we can know only height, but we cannot know if there are two different kind of materials. But through the lateral force microscopy, we can able to tell there is a inhomogeneity in the sample or there is two components in the sample, like that you have seen in the phase imaging. But here it additionally provides the friction properties of the sample, and this is done in the contact mode. The phase imaging was done in tapping mode or non-contact mode when tip oscillate, but for lateral force microscopy it has to be done with contact mode. The tip has to come with a constant load and contact the sample surface, and then see how much horizontal bending of cantilever is occurring. And this is what you see in the graph in the regular topography FM image. This is a regular topography image. We locate the displacement of cantilever in the upward or downward direction. Therefore, from the reflected laser light here we will know up and down, and this is what the topography image. And if we put the position sensitive detector with that 4 quadrants, then we can see that frictional information can be obtained. Like here is a horizontal moments, as you see the tip is bending in the horizontal direction here, as tip is bending horizontal direction, the reflection is not in upward direction, not only in the upward direction, but also in the horizontal direction. So, by measuring the deflection in the horizontal direction, we are measuring the lateral force or frictional force, and this is what is done in the lateral force microscopy or frictional force microscopy. And if you see here an example shown in the schematic diagram, here in the left side the height remains same here, the height remains same here, but there is a different material here, additional another material which is given in the different color, height remains same. So, in the regular topography image we will not see any contrast difference but if we take a lateral force microscopy, we will measure the lateral force because of the horizontal deflection, and therefore we can get a image due to its frictional properties. Now, you see the surface is like this, we have a upward features here in the middle, and therefore, in the surface when we do regular topography image, the height remains same. The signal, as you see, these are surface signal, it is a surface, and the AFM signal, as you see in the AFM signal, height remains same. As height remains same, there is no signal here, no signal, only the signal come when there is a height changes. But in the lateral force microscopy, what you see, there is a signal. In this position there is a signal because this is the places where we have a different sample and its frictional property is different to other places. Therefore, we get a signal here or we get a different contrast here because of inhomogeneity in the sample. Then what we see there is a edge, when there is a edge happening, and if it is in upward direction, because tip is moving, scan direction is moving like this, that is a convex type of features, that means upward direction the tip is moving and then it is becoming flat, and then if it is downward, here it is a downward movement of the tip, then it is in the concave or downward direction, then it is going flat. If we scan direction is opposite, then as it is seeing a upward, here it is seeing a upward object with upward features, therefore, it is going with a convex peak and here is a convex peak, and here it is in opposite direction, the signal is coming opposite direction. So, both lateral force microscopy we can see a difference in the contrast because of the change in the either height and also, and here there is a edge, as you see that this contrast is due to the edge of the features and this contrast due to the frictional features, frictional or the change in the frictional properties in such region because of two different sample. So, this is what a lateral force microscopy gives us. I can show you with an example. This is the example we have seen before, the graphene films. This is a topography image with a topography contrast. This is the scale bar of topography constant. This is a phase contrast. We have seen that how phase image giving us more information, which we could not get with a height image. We cannot, from the height image, it is not possible for us to know which is one layer graphene, two layer graphene, and the buffer layer graphene. So, phase image could gives us this information. Another interesting things you can see in the frictional properties. Frictional properties, not only you see three different contrast, like one contrast is due to this very bright contrast. So, at bright constant we measure a higher frictional, higher deflection, higher frictional coefficient. So, deflection is more, the force acting on the tip is more. So, we see higher frictional force. Then second most is coming here, frictional force is one layer graphene, and third one is here two layer graphene, one layer graphene, and the interfacial layer having three different contrast. In addition to that, you see a much brighter interface edge. As you have seen in the previously, when we see an upward features, we see edge, convex or concave edges, and this contrast is also clearly seen when a one layer graphene is changing its position to another because of this is schematic diagram. At this edge we see a quite high contrast. In this way, frictional properties of the sample, inhomogeneous sample, can be measured, and we can tell that means the sample there is a inhomogeneity in the sample surface, which sometimes cannot be detected from the topography image. So, in addition to this horizontal deflection, one can also do shear measurement, like we can do shear modulation force microscopy. In the contact mode, we put a constant load force, and then when we scan on the surface by through a raster gun, due to frictional force we see a horizontal displacement. Now imagine you put a constant pressure, constant force, and after putting a constant force, then you make an modulation in the horizontal direction. Put a vertical force, then make a horizontal direction modulation at the same places. So, this is called shear modulation. So, shear modulation involves engaging the AFM tip on the surface with a constant normal load, followed by, after putting a constant load, followed by oscillating the probe in the horizontal direction. Remember, in a dynamic mode of AFM, we were doing vertical modulation, vertical oscillation. In this way we are doing, and we are seeing the amplitude change or frequency changes in our dynamic mode of AFM operation or tapping mode of AFM operation. Here what we are doing, we putting a constant force in the constant in the contact mode of operation, and then doing opposite horizontal modulation. And this modulation, we give a particular modulation, and then we study that what is the response in the modulation. One modulation we give, and we see what is the response modulation. That is what is done. So, as you see in this graph, a constant force is applied, then after putting the constant force, a particular modulation in horizontal direction or lateral direction, we give modulation and study the response modulation. That is why del xr is given here. The lateral modulation, response modulation, del xr. So, this is this can provide us the viscoelastic properties, viscoelastic properties of the sample surface, and it is particularly used in the phase transition in ultra thin polymer sample. So, I will give an example how the shear modulation force can be applied to determine the glass transition temperature in the polymeric sample. Now, what you see here that measurements of glass transition temperature using shear modulus force microscopy. So, you know glass transition temperature is the temperature below which sample is hard and brittle, and above which sample is rubbery or molten. So, below the glass transition temperature sample is very hard. As sample is very hard, penetration depth will be less, and doing this lateral modulation or is difficult. But on the other hand, when sample goes or sample is above the glass transition temperature, sample is, as I say, this is no more hard, rather it is rubbery or molten. Therefore, penetration depth will be more, at the same time it will be giving more horizontal or lateral modulation amplitude. So, by measuring that modulation amplitude here del XR versus temperature, one can know the glass transition temperature. In this case particularly, this is for a polystyrene film, and this is a thickness of the polystyrene film have thickness of 200 to 300 nanometer with a different molecular weight range 3 kilogram to 6.5 megagram. So, the polymer softens above the glass transition temperature, that means it become molten or it become rubbery. That results in larger penetration and larger amplitude, that is a larger or higher lateral amplitude. As you see, we have two different in this curve two different slope. One slope is going here, another slope is going here. So, these two slopes, these two curves, these two lines are intersecting here, and this is the temperature at which that is called glass transition temperature, at which a hard and brittle material becomes soft and rubbery material. So, this is the glass transition temperature. We can measure the glass transition temperature using shear modulation force microscopy in the AFM, and it has been found that the value of glass transition temperature of the surface is almost matching to the bulk sample, and bulk sample glass transition temperature is measured with a differential scanning calorimetry. Normally glass transition temperature are measured with differential scanning calorimetry, but that is for bulk sample. If we have a thin film or you have many interface layer and we want to accurately measure the surface glass transition temperature, then such measurements cannot be possible directly by the differential scanning calorimetry, because differential calorimetry sensitivity depends on the quantity of the materials, and the sensitivity will not be high if the material is very thin on the surface. So, thin film polymer measuring the glass transition temperature by thin film, a polymer in a thin film form is difficult in differential scanning calorimetry, which can be measured here. And in addition to that, as we are putting a force here in a soft sample with a particular load, that load is supposed to should be not very high, because very high load also can damage the polymeric sample. We can measure the lateral amplitude, and the distinct change in the slope of the temperature versus amplitude curves is used to identify the glass transition temperature. We have other force microscopy that we will discuss in the next lecture. Today we go to conclusion. We have discussed on the two different long range force, that includes capillary force and electrostatic force, and how capillary and electrostatic force can also be measured using atomic force microscope. And then we discussed lateral force microscopy and shear modulus force microscopy to study the viscoelastic properties of the materials, particularly the materials we has both viscous and elastic properties, particularly for polymeric sample. These are the references.